Okay, review time. This might even be the last video that I make for this year. I'm not really sure. It might be. Okay. So, we got three standards. First one is 8AB. Students know what a rate of reaction is and how to speed up or slow down the rate of reaction. Well, I guess first off, we should define rate of reaction. So this is how fast a reaction proceeds. How fast reactants are used or products are made. For the forward reaction, which is typically what we assume. Okay, what about this one? How to speed up or slow down the rate of reaction. Well, we know that for something to react, they've got to collide, and they have to collide in the right orientation. So anything that creates more collisions or helps the orientation will speed up a reaction. So you could increase the temperature. That would make them move faster. They'd collide more. You need to be able to explain that though. You can increase the surface area. That'll expose more of the reactants together to each other, and they'll collide more and create more product. You could agitate. That's going to force them together. You could increase the pressure for a gas. That's going to literally push them closer together. Or decrease the volume. Those are kind of two ends of the same coin. That doesn't make sense. I don't know. You could add a catalyst. That's going to decrease the activation energy. We'll get that to a little bit. It'll speed up the reaction. Okay, so make sure you can explain each one of these. I'm not going to do it. I feel like I've reviewed enough. You should be able to explain based on collisions. So if I have you write something out, you've got to take it back to collisions. See what I did there? Collision. Collisions, but it's got to go in the right orientation. Okay, this next one, 8CD. Students understand activation energy and catalysts. Well, what is activation energy? Activation energy, the energy needed to start a reaction. So in your car, this is, the starter, the ignition, the spark plug. You've got gas, which wants to explode, but it's got to have a spark to get started. Or it's like your candle, which you've got to light a match to get started. But once it gets going, it's going to keep going because it's producing its own energy. It's exothermic. So what's a catalyst do? Catalyst lowers the activation energy, speeding up a reaction, and isn't used in the process. So it's not a reactant, it's not a product, it's not used in the reaction. Oops, sorry guys. Grabbed the wrong thing there. There we go. So the best way to visualize this is with a graph of the energy of a reaction versus time. And so it'll look something like, for an exothermic reaction, it looks something like this, because it loses more energy than it starts with. And then when you catalyze it, it's going to take the activation energy down. So now it takes less work to get over this little hump. So it's going to take less work to get the reaction started. And the reaction is going to go faster. Okay. Just like if you live closer to school, you get to school faster. It takes less work to get there. If you have to go over a giant hill to get to school, it's going to take you longer than if you go over a small hill. And students can explain chemical equilibrium. Okay, well, what's our definition? Chemical equilibrium. When the amount of reactants and products is constant. Constant, not equal. That's a big difference. I'll have to explain that again later. Is constant because the rates of forward and reverse reactions are equal. Okay, so let's say we have an example reaction. We've got I don't know what the reaction is. Let's just do letters. It's kind of a cop out, but whatever. We'll do A plus B, double arrow, so it goes reverse and backward and forward. Okay, A plus B goes to C. This is going to reach equilibrium when the amount of A and B turning into C is the same as the amount of C turning back into A and B. So if I had 10A and 5B and 3C, they're not equal to each other, but it could still be equilibrium if 10 and 5 make 3, and then 3 goes back, and, well, not 10 and 5 make 3, sorry, but I use 1A, 1B, and I make 1C, and then 1C breaks down and makes 1A and 1B, replacing the ones that were used. So nothing actually changes because the rates are equal. That would be chemical equilibrium. So I'd say the hardest part of this unit is probably right here. That's where you're actually explaining something that I don't know that I prepared you too well for. It's very similar to rate of solution. So you can go back and review those notes if you want. This one has to do with how fast the particles are moving, how broken apart they are. This one's kind of obvious. And this one's new, but there's enough reading on that. Okay, so make sure your homework's done, all 2 pages of it, and I'll see you in class. Bye-bye.